Hi guys, thanks for enrolling to our course on the introduction of mud crab vertical farming. In the previous lecture, we have shown you how to design your own foam fractionation and what is the design criteria as well as the mode of operations. In this lecture, we will be talking about biofiltration. Biofiltration remains the heart of any RAS systems and is often the limiting factor in scaling up your aquaculture business. A good understanding of this biofiltration is crucial to ensuring that your crabs are being able to feed at a high rate as well as a low mortality. We will split this lecture into two sessions, with the first session being the theory of nitrification, and the second portion will be how to size your biofiltration plant accordingly. Biological filtration is a process that has been used for hundreds of years. The typical application for biofiltration is in a wastewater plant. On the picture over here, we see that this is a municipal plant in which bacteria is used to break down the waste into lesser harmful form before discharging into the environment. It is commonly found in the wastewater industry, the palm oil industry, and even your small size aquarium on a residential home. However, the difference between the hobbyist and actual aquaculture farm is the magnitude and cost effectiveness. Very often, aquariums at home are oversized, but because due to the cheaper costs in relative to big aquaculture projects, it is usually gone on unnoticed. However, biological filtration is an expensive plant to maintain and it will form one of your most expensive capital cost items. But the goal of the biofiltration is to treat the dissolved matter derived from uneaten feed and feces, which manifests itself as ammonia. The concept of biological filtration is what we call nitrification. Note that there are a lot of terminologies for the same thing. And a nitrifying reactor or a biological reactor is simply where this process takes place. An important concept about nitrification is to provide enough surface area for the bacteria to grow on. And we have to also provide them with adequate food, good living conditions, and protect them against competition against other types of bacteria. What we have here from these three pictures are all what we call biological media. They simply can be made up of plastics. In this is what we call the traditional bio balls, and this is what we call K1 media, and this is what we call ceramic media. Essentially, they provide plenty of surface area for the bacteria to reside on and repopulate, as well as consuming ammonia into NO2 and NO3. Having that said, biofilters is essentially where nitrification takes place, and it's all about providing them with the necessary surface area for them to grow and thrive. They can come in many shapes and sizes. Note that you can also build your own bioreactor. You just require a tank and some media for the bacteria to go onto and adequate aeration, and bacteria will definitely grow. However, selection of different reactors will depend on several objectives, and it will often depend on your feeding rate, size constraint, and oxygen availability. The goal of biofiltration is to convert ammonia into a lesser harmful form. So where is all this ammonia coming from? We have feed or fecal matter that is consumed by the crab or is produced by the crab, which will slowly dissolve in the liquid, which in our case will be the system salt water, and that will often form what we call ammonia. Ammonia is very toxic and it needs to be kept as low as possible. The values that you should be targeting is 0 to 0.25 ppm. The goal of biological filtration is to convert ammonia into NO2 and NO2 to NO3. And how do we do that conversion? Ammonia is a food source for a type of bacteria known as Nitrosomas. It is commonly known as a nitrifying bacteria. So what does this bacteria do? It consumes ammonia and with the aid of oxygen metabolizes ammonia into the next form, NO2. And then NO2 is used to feed another bacteria called Nitrobacter, And when you provide Nitrobacter with oxygen, it is able to consume the NO2 and produce NO3. Is NO2 and NO3 harmful then? That's a valid question. NO2 and NO3 are known to be less harmful as compared to ammonia. So your goal of nitrifying is to convert ammonia to NO2 and NO2 to NO3 in the fastest times possible. How do you estimate the amount of ammonia that is going to be produced? Total ammonia production, which is the ammonia that is harmful to the crab, is a function of feeding rate, how much feeding rate we are feeding a day, and it's also a function of the protein content in the feed. Typically for trash fish, higher quality trash fish could mean up to 40% protein, while high protein fish meal can sometimes reach up to 60 to 75%. These are the two building blocks of where are your ammonia coming from. We have also other parameters, for example, how much ammonia is actually being released into the water, which is a function of your solid filtration, the type of crustaceans or the type of species you are farming, and this is a typical conversion rate to convert protein into ammonia. So let's look at a quick example. We have to estimate the total ammonia nitrogen produced by 10 kilo feed at 40% protein content. So assuming if you are feeding 10 kilos of feed every day, what happens? 10 kilos of feed multiplied by the protein content multiplied by the wastage, which is a function of your solid removal and your species of interest, and these two are just conversions. We can see that 10 kilos of feed will produce approximately 0.4 kilos of total ammonia nitrogen on a daily basis, which is approximated to be 3% of your total daily feed rate. And this is producing with feeding 10 kilos of feed at 40% protein. So what happens if we change to a higher protein source feed? There can be feeds that are high in protein such as BSF or even high protein feed. As you can see, feeding the same amount of 10 kilos of feed every day, but the only thing that changes is the protein content. My total ammonia nitrogen comes up to 0.48 kilos a day, which is approximately 5% of the feeding rate. So what happens if I double up the feed amount 20 kilos while keeping the protein content constant? As you can see, my total ammonia generated is 0.96 kilo of feed a day. So what is the takeaway value of this? The ability of the biofiltration to control ammonia is only dependent on the type of feed and amount of feed that you'll be feeding in. Assuming that you are not able to control ammonia, the best way is to stop feeding, and the water quality will slowly get back to its original value. So why is total ammonia nitrogen important? Firstly, it determines how much biological surface area do you need. What do I mean by biological surface area? Biological surface area simply means the amount of media that you require to treat an amount of ammonia. So what is the design criteria? Firstly, you need to ask yourself, what is your objective? Are you trying to do fattening, soft-shell crabs, or grow up? Having that objective stated, you then move on to decide how much you have to feed on a daily basis at the maximum capacity. For example, assuming that you have to feed your 1 kilo crab at 10% of its body weight, it means that on a daily basis you have to feed your crab 0.1 kilo, which equates to 100 grams of fish. You use this feeding rate and estimate how much total ammonia nitrogen you will be generating, and then you estimate the amount of biofilters you need. It is very important to understand that nitrification in different salinity reacts differently. For example, you cannot just use the nitrification rates in the freshwater and apply it to the seawater, because in seawater, nitrification is much slower. It is estimated to be 40% in reduction rates as compared to freshwater. This is the volumetric nitrification rate in freshwater and versus saltwater for the same bacteria. As you can see, most of the coefficients are the same, but there is a constant in front of the saltwater, which is 0.5 as compared to a 1.1 in freshwater, suggesting that freshwater nitrification is almost twice as fast as salt water. So it is very important for you to estimate biological filtration in a saltwater basis. That's all for now. In the next lecture, we will talk about the different techniques used for nitrification and the different reactors that are available in the market and their corresponding nitrification rate. We will be designing your system based on the amount of feeding rate that you will be providing to your crabs.